This is an explanation of the VGGT paper that came out in 2025. First, let's take an overview. And full name of VGGT is Visual Geometry Grounded Transformer. It was a paper published by Meta AI. In the first figure of the paper, it shows the problem this paper is trying to solve. So on the left side, and the input to the system is multi-view images. So a list of the images from different view angle showing appearance of the same thing. Then the image set was fed into the transformer, this VGGT transformer. The output include first 3D point cloud. This is a dense 3D point cloud, shows the 3D structure of the scene. Second, it also output all of the camera parameters, which include both the extrinsic and intrinsic parameters of the camera corresponding to each of these input image. And for each of the camera, its corresponding depth map with respect to the camera location. And also it also output point track, which means give a list of these images, and if a query point is provided, the algorithm can output the corresponding point of this query point throughout all of the images in the sequence. Basically, by looking at this first figure, we see that all this algorithm is trying to solve include almost everything that that people ever want to know in multi-view geometry. So, but the paper is trying to calculate all of this output using a single transformer network. This paper won CVPR 2025 Best Paper Award. It treats the transformer latent space itself as a structured geometric word representation. As we saw in the previous slide, the input to the network is very flexible, include like one image, a few images, or even hundreds of input views of the scene. So this is a very flexible requirement to do the multi-view geometry, because in the classical method, like at least two view has to be provided, but here like any numbers of views is possible. The output include a full stack of all of the stuff that people ever need to know about a scene, like camera parameters, depth map, 3D point cloud, and point tracks. This point track is what we mentioned, like track the corresponding point throughout the image sequence. The paper claimed it performs 3D reconstruction in a single forward pass in second. So this is a very strong claim. So as we all know that any people study in computer vision field must have read the textbook written by Hartley and Zizerman, this multi-view geometry in computer vision. So we may spend years of hard work study everything explained in this kind of textbook and trying to understand how to do the multi-view geometry, how to estimate the epipolar line, epipolar geometry, find the correspondence, extract feature point, do triangulation, bundle adjustment. After we understand all of this stuff in the textbook, now we see this claim that there is an algorithm that can perform 3D reconstruction in a single forward pass in seconds. So I think this is a very astonishing claim to any person in the computer vision field. Next, we take a look at the problem formulation. So this was explained in figure 2. In figure 2, it appears this is quite clear structure. So the input is a list any number of the image sequence of the same thing. Then the author choose a dyno to patchify the input image into tokens. So the dimension of this is like if k is the number of the tokens, then for each image the dimension of the image token should be k by c. C is the feature space. That means each patch was represented by a token which is a vector with a dimension of c. So altogether image will be represented as a matrix with dimension k by c. So once this image are patchified by dyno, it was turned into image tokens. Then each image was appended with a camera token. This was fed into the what is called alternating attention module. So it basically alternating between global self-attention layers and frame-wise self-attention layers. This attention model basically sequence in, sequence out. So if there is a list of sequence fed into this module, the output are the same number of these token sequence. But after it come out, these tokens will be rearranged to camera tokens and image tokens. For the camera tokens are fed into a camera head, then make the camera head will make the final prediction for camera parameters, which include extrinsic and intrinsic camera parameters, and the image tokens are fed into a DPT, which is dense prediction transformer network, to generate depth predictions, so which include the two parts. First is a depth map, then second is this 3D point map. And the image tokens are also fed into a co-tracker 2 network to generate the tracks, which can be used to find the corresponding point throughout the image sequence. So overall, if we are trying to understand the input output and its dimensions that VGGT use, then here is a summary. So input is a sequence of n RGB image. So n is the number of the images. For each image, there are 3 channels RGB and the image height and image width. VGG network basically is trying to find a mapping which maps image sequence into a list of output. So first output is camera parameters, which is represented as GI. So GI is a vector, is a non-dimensional vector which consists rotation, which has 4 dimensions, and the translation 3 dimension, field view 2 dimension. So altogether, the camera parameters was represented as a non-dimensional vector. The second output is a depth map. So for each image, there is a depth map corresponding to that image, corresponding to the depth from that orientation, camera orientation. So the depth map has the same dimension as the image. And the third output is 3D point map. So for each observed pixel, it is corresponding 3D location in space. So which is a 3-dimensional point location, include x, y, z coordinate. We also note that all of this 3D point map was defined in the coordinate system of the first camera, which was taken as a world reference frame. Then the last output is the C-dimensional features for point tracking. So basically, this is what output from the VGGT transformer. It output image tokens which has the same dimension as input image tokens, but now it encodes the geometry structure. It has a dimension of C by H by W. This transformed image representation can be used to find the corresponding point, the point tracks through the image sequence. By looking through this set of input and output, we notice that the author chose to use overcomplete predictions as output to this VGGT network. So for example, giving 3D point map, then use traditional perspective endpoint method, we can derive the camera parameters G, and also give 3D point map and the camera parameters G, we can also derive the depth map. So the set of the output is over complete, but they choose to generate this for output. That is because first author observed that during training, this setting brings substantial performance gain. Second, during inference, combine independently estimate depth map and camera parameters, produce more accurate 3D point. So we also see this table 6 in experiment part, which shows that the author actually did ablation study. It's kind of quite exhaustive. Ablation study they tried different combinations of these output settings with or without camera parameters, with or without depth map or the track. So they tried all of these 12 combinations, and then they observed that with the current settings, these 4 output, the algorithm achieve the best performance. So this is what this paper used. Next, we focus on the network design. So the main contribution of VGGT paper, the in terms of network architecture, is they propose this alternating attention module. So it consists of global attention. So global attention means every image token attend to all of the tokens in the input, include both the tokens from the same image and also any tokens from any other image. It also has this frame-wise attention, which for each image tokens, it only attends to the tokens within the same image separately. So this image token only attend to the tokens from the same image frame. There is no cross attention layers, and also this AA attention module eliminates frame index embedding. Here I take an image from the presentation that the author provided. So I think this elimination of frame index embedding is a very smart and appropriate choice to this problem, because in multi-view geometry settings there is no image 1 or image 2, which means the image sequence order is not semantic meaningful. It's not like during the when we turn an image into patches and turn it into image token, we sometimes append positional embedding, because that the first patch and the second patch, the first and the second has semantic meaning. The first patch is always start from the top left, and the second would be next to that first. But for this multi-view image sequence in these settings, the frame 1 and frame 2, they do not have semantic meaning, so we cannot like embedding to add a positional embedding like position 0, position 1. It's not like this image is in front of that image. So it's trying to learn a globally consistent geometric latent space over arbitrary collection of views. And also because this algorithm is very flexible about the input, so any number of the image can be fed into this network. So this also, by eliminating the frame index embedding, also allow this flexibility to the number of the images, to the number of the input images. Like this picture also shows clearly, if we add the frame index embedding, like this is the image 1, 2, 3, then we feed this list of the images to the model, we may get a different model versus like we feed the image 1, 3, 2, because the input is different, because this image are added with different frame index embedding, so end up with different model, but that is not true because it's a set of the image instead of the ordered list of image. As we mentioned, the input to this system is quite flexible. It takes any number of images as input, so the algorithm needs to handle variable length sequence. As we see, like all patches which are patchified use Dino V2 and concatenated together. Then during training, basically the network did this sequence length augmentation, so it sees monocular samples and also stereo pairs, sparse multi-view, dense video clips. So this training process basically let the network learn camera baseline, overlap ratios, ordering sequence length. The transformer learns single view priors and pairwise geometry, as well as long range multi-view consistency. We can also take a look at the detailed structure of this alternating attention transformer architecture. The input token consists of image token, camera token, and also there are 4 register tokens. So image token that depends on the size of the image and the size of the patch. Then for each image there is a list of tokens. Camera token will be represented as like C prime is a feature dimension. Camera token, there is a single camera token. There are 4 register tokens. These tokens were fed into alternating attention transformer. Then the output tokens has the same dimension as input tokens. For this register token, this register token was first proposed in this paper, Vision Transformers Need Register. Here we also briefly describe what is the register token. So from this image, we see clearly that the idea is straightforward. So for input image patches, normally we append CLS tokens to the image tokens and feed this into the transformer model. Then from the output side we collect this transformed image tokens and CLS tokens as output. The so-called register token is just similar to append CLS tokens to the input. We also additionally append, like for example, 4 register tokens. Then on the other side, on the output side, we discard these 4 register tokens, and the rest just works as a regular transformer model. So this this looks a bit like strange. Why? We add some register tokens, and on the other side we just disregard them. So the paper claimed the vision transformer sometimes use background tokens as internal memory workspace. Adding these dedicated register tokens improves dense spatial output, and smoother attention maps. By adding these register tokens, if we look at the result, so we input different kind of the image, and we look at for different network, we look at the attention map. So we notice there are some like bright spot on the background. This is not what we want, because for the what this attention map mean, attention map is like so this image normally has a foreground and background, and the network was trained, like most of the network was trained use a CLS token, which means it extract the higher level object level category of the image. So if we look at the attention map, the foreground object should have high weight. So this attention map will be the weight corresponding to the value. So the foreground pixels or patches should have a high value, while background patches will have a low value. But now, like background patches shows a high value. That means in assigning weight, background patches were assigned maybe a weight that is not appropriate. With if we add these register tokens to the transformer model, then we see that everything looks clear. Background like has evenly like dark, should appear as evenly a dark region, and the foreground has a high intensity, indicate foreground will be assigned higher weight when calculate the attention. So basically this was observed merely adding a few learnable latent tokens significantly improve representation quality. So that is why register tokens was introduced. Let's go back to the VGGT paper. This slide shows how the reference anchoring happens along together with the reference token. So here are a list of input. This is the first frame, second frame, until the nth frame. So in order to, because all of the output was 3D point coordinate were generated in a common coordinate system, which respect to one of the image. That image is called reference frame. So the camera token and the register token of the first frame are set to a different set of learnable tokens. All other frames were set a second set of learnable tokens. So here is what this means. So for frame 1, this is a reference frame. This frame needed to be identified from the network structure. How to identify this? Because this frame was assigned learnable camera tokens, and this is called reference camera tokens, and 4 reference register tokens. Then the rest are the image tokens. For all of the frame 2 to frame n, they are assigned a shared camera tokens. So these camera tokens are shared, and 4 shared register tokens. So that's how the algorithm differentiate between the reference frame and the rest of the other frames. On the output side, so as we mentioned, there are three parts of the output. First, we look into the camera head prediction. So after the alternating attention layer, we collect a list of tokens, which consists camera tokens, register tokens, and image tokens. We discuss register tokens and was left with camera tokens and image tokens. We collect all of the camera tokens and feed them through this camera head. The tokens come out from the AA module has the same shape as the input. So C is the feature dimension, but now after this frame-wise, global-wise attention layers, alternating attention layers, these tokens now contains geometric aware latent descriptors. So there are still like input contains n frames and output also contains n frames. That means n camera tokens. These tokens feed into the camera head. This camera head contains 4 additional self-attention layers followed by a linear layer. All of the n cameras was fed to the camera head independently. Basically, the camera head is just a mapping which maps C-dimensional tokens, a single C-dimensional tokens to a 9-dimensional feature vector. This a stack of camera tokens does not mean anything happens this attention layer. Anything happens in the attention layer that lacks one camera to attend any other camera. They are all independently fed. This stack only means maybe to save time they have a parallel calculation, but they are all independent. No one attend to anything else at this stage. So this camera head is a simple mapping from C-dimensional vector to a single non-dimensional vector. This non-dimensional vector is what we need, which are rotation, translation, and field of view. A list of the camera parameters. The second part of the output are the dense output. So first we need to have a brief review about this DPT, dense prediction transformer. The dense prediction transformer was also proposed by Meta. So it was used to predict dense output by using multi-skew fusion and extract multi-level features from using the transformer. The DPT can provide sharper boundaries, and because it uses transformer, it also can maintain large structure consistency in their prediction. So if we look at the DPT paper, vision transformers for dense prediction, figure 1 in that paper shows clearly the structure of the DPT head. So the image was partitioned into non-overlapping patches and get image embedding. Besides the image embedding, which was represented as like orange vector, a red vector, which is called patch independent readout token, was also appended. So I think this is similar to the CLS token. These tokens was fed into levels of transformer module. Then in this green box, this called reassemble module. This green box takes one input and generate one output. So this green box was further explained here. One input, one output. So the image token plus one, like this kind of CLS tokens was fed into a read layer. So this read layer generally maps this NP plus one tokens into NP tokens. So that means this CLS tokens was absorbed to the transformed image token. Then this image tokens was catenated, reassembled. Remember, like when we patchify the image, we flatten all of the patches. Now we reshape this image tokens to its original location. So now after this assemble, it more look a convolutional network type of thing. Then bypass it through different projection layer, resample layer, the shape of this tensor changed to the desired shape. Like there are several layers. It basically performing multi-resolution projection. So this S represent the degree, the level, the resolution level that the layer is supposed to generate. So this is multiple resolution layers. Then after this resample module, we come to this fusion multi-level, multi-scale fusion module. So this purple module takes two inputs and generate one output, which further explained here. Two input and one output. It's also like convolutional type of stuff. It like some residual conv net unit and upsampling by 2. So this resample 0.5 means outsample by 2 projection. So each layer, the fusion module upsample the feature dimension by 2. Then it fills with the finer level features by doing this multi-scale fusion, and finally pass a projection head, get this dense prediction. So let's go back to VGGT. Besides these, VGGT uses structure. So given all of the image tokens come from the AA module, these image tokens, camera tokens were fed through the camera model, image tokens fed through DPT module. DPT module basically, it uses DPT modules to transform the image tokens to the dense feature maps with a dimension of C prime prime by H by W. Then for different output, so there are 4 output. They append light-weighted projection head to generate the first output is a dense depth map. Second output is uncertainty associated with depth map. They have the same output dimension. Third output is a point map. For each point, it's a 3-dimensional vector like x, y, z coordinate, and also there is a uncertainty associated with point map. Note that this uncertainty has the same, the dimension is h by w. That means uncertainty is not what we normally understand, like in order to represent an uncertainty of a 3D point, we normally need 3 by 3 covariance matrix, but now the uncertainty is only represented as one scalar. This uncertainty basically indicates the regions like occlusions, reflective regions, texture surfaces, this kind of difficult regions in the image to indicate how reliable our 3D point estimate is. Like we previously mentioned, each image independently output a dense cloud of 3D point in the same coordinate system. That is where how the algorithm handles variable length input image sequence. For example, if there are 3 images are fed into this DPT module independently, similar to what happened to the camera head. So all of the images are fed into camera head and fed into the DPT module independently. So there is no image attached to any other image. Because for each image, this here this orange, green, and blue represent 3 images. For each image there are 3 image tokens. They are output from the AA module. In the AA module, those image tokens has already gone through the global attention and frame attention, so they has already attended to other frames and other patches within the same frame. So now they has already encoded all the information, all the geometry information, in order to understand its orientation or position of entirely 3D structure of its part within the entire image sequence. So now they don't need to take anything into consideration. They only need, for example, these 3 orange image tokens. They are also from the same image. Now they only need to be fed into the DPT and generate its own depth map. The last output is this track head. Track head is just the output image tokens from the A module. In order to, this cannot be directly used to find the tracks of the image of the point correspondence. It has to be fed into this co-tracker network. So this co-tracker network was described in the paper, code tracker is better to track together. The main point generated by this paper is, instead of tracking each point independently, track many points jointly. Use a transformer is better, which runs attention across point time frame. So points means normally we extract in the classical computer vision literature, we extract a point, then match point in another image independently. So now a bunch of pretty dense, a bunch of point was extracted, and this point I extract from the same frame. Then these points are tracked together, because if these points are all on the same object, they tend to move in a similar track. So if we can capture the main trend of this set of points, then we can get a more reliable estimate of this correspondence. So that's point need to attend to other point, other nearby point, and also one point need to attend to the same point in the across the time. So because this paper also address track features through an image sequence or video sequence, it's more like an optical flow way of tracking, and also point as what we need in VGGT, point need to be tracked through image sequence. So these are also a transformer architecture. Input is a track query, so like the network can track simultaneously k query point. So k is the number of the query point. D is a feature dimension because it will use the image token as input. So this D is a feature dimension come out from the A module transformer. The output is k, this queried k queried point. It's a 2D location, image location through all n images, and also it generates output called visibility, indicate if one point is occluded or not in one of the image. So the main idea was proposed. There are a series of papers developed from like code tracker 1, 2, 3. The main idea was proposed in code tracker 1. Like we mentioned, it trying to solve the tracking problem across temporal windows. Also, it introduced proxy global tokens instead of full all attention to save computation cost. Then more improvement was made to code tracker 2 and code tracker 3. I guess the main idea is to learn persistent motion tokens over space and time. So it's in the VGGT paper, we can just treat this code tracker 2 as another transformer module. And the output from the VGGT transformer is like a C by H by W image tokens. These image tokens were fed into the code tracker tool and get the tracks. So if we represent as a formula, so query, there are the Y is a pixel location, a two-dimensional pixel location, and there are M query point. Then this is a track come up from VGGT. The query point can be floating point. Then given the floating point, then linear interpolation can be performed to get its embedding. It's a patch embedding. So this is a grid of patch token, image token. Given these two input, the code tracker is a transform, is a mapping that map this input to output, which corresponding to the M query point, its location, 2D location in all N images. So this result shows two cases. One is the images corresponding point are tracked through unordered image collections. The second is the feature point are tracked through a video. I think this is a video. Now let's see how this network was trained. The training loss need to consider all the output we collected. So camera, which consists camera prediction, and the point maps camera prediction constraints depth, point maps constraints geometry, and the tracks constrain the corresponding consistency. So the loss function consists of 4 terms. First term is camera loss. It's just the ground truth camera parameter minus predicted camera parameter minus ground truth camera parameter. Then they use Hoover loss, sum them up. So it's pretty like straightforward difference of the camera parameter prediction. Second term is depth. It's also the difference between the predicted depth map and the ground depth map. And this difference is weighted by the uncertainty. Also for depth, not only the absolute depth map matters, the gradient of the depth map also matters because it shows the depth discontinuities and the object boundaries. So the difference of the gradient of the depth map also calculated and weighted use the uncertainty. And there is an uncertainty regularization term. The point map, 3D point map, follows a very similar structure. The difference between the ground truth 3D point weighted by the uncertainty. Also the gradient, the difference of the gradient of the point map weighted by the uncertainty plus a uncertainty regularized term. The tracks is just the distance between the ground truth point location and the predicted image point location. we notice that there is only one scalar is added to balance all the four terms. It looks like the rest four terms don't need any parameters to balance their magnitude. So only lambda is introduced here to balance the magnitude of these terms. The paper also shows some implementation details. So given the ground truth, we can calculate the average Euclidean distance of all 3D points to the origin. Then use this as a scale to normalize the coordinate. And during the prediction, the normalization of prediction output was learned. The input image are isotropically resized to keep the longer size as 515. So we see that this input image size is not very large. The training runs on 4064-800 GPU over 9 days. The training dataset, but this is where heavy lifting work happens. By reading these 15 lines of description, we see that the model was trained to use a large and diverse collection of datasets, include all of this dataset. From this, we see this is where heavy work occurs. There are tons of network dataset. So first, a lot of work need to be done to figure out what these dataset are, how to use them, formulate this dataset in the right format, in the right shape, and feed it to the network. Second, in order to build each of these datasets, the ground truth need to be collected. The ground truth contains camera parameters, ground truth depth map, ground truth 3D coordinate, and the ground truth point corresponding point. There are a huge amount of work involved in this simple 15 lines of description. Dataset consists of 3 types. So first is synthetic data. Synthetic data turns out it decreases generalization because image were created. Those created image would look different from a real image, so it will generate a decreased generalization. The second type of the data was generated with pseudo-label, and this is what is mentioned here. So the annotation was generated either direct sensor capture, synthetic engine, or SFM techniques. So this pseudo-label means the ground truth data was generated using other SFM algorithms such as COMAP or some other method. Because those method itself contains noise, so it decreases accuracy, but it increases generalization because it's used real image that were generated by take the real camera and capture the image of the real thing. Third type is labeled data, which is a direct sensor capturing, which is sparse, and the condition like one we can use direct sensor caption is pretty limited, so the data collection is sparse. Now we come to the experiment part. In experiment, all of the 4 output was evaluated, which include camera pose, multi-view depth estimation, 3D point map estimation, and image matching accuracy, in order to evaluate all the quality of this output. The authors need to find different sets of metrics, and besides the accuracy, we also need to evaluate the efficiency of the algorithm to compare the calculation time, and also a lot of ablation study was performed to validate the network design, like how useful is this alternating attention, how with or without cross attention and overlap output, like why the author chose these 4 set of output. There are a lot of ablation study to validate each of these network design. Overall, the conclusion is the algorithm is faster, more accurate, and work with less input. The author also experiment with fine-tune for downstream tasks. Tasks include the feed-forward, novel view synthesis, and dynamic point tracking. In figure 3, author shows 3 examples. First, these 3 examples are all extreme case, as I understand. So first is a single view oil painting. So normally classical computer vision need at least 2 images. Now there is only single view, and it's oil painting. VGGT is even able to generate 3D structure of this of 3D scene from a single oil painting, which is definitely impressive. Second example is 2 input views, but the problem is this 2 image has no overlap. If we look at the output, this part and this part has no overlap, so how the algorithm is able to figure out like this part and this part are the same, I should be aligned together. So it's not obvious that even by some alternating attention, it's still hard to understand how the algorithm is able to figure out these 2 parts should be aligned. The third example contains 32 views, but it's like a pyramid, contains less no obvious feature point with like a smooth texture. The structure of the pyramid was accurately recovered, and also VGGT was compared with other method. This method also get the pyramid structure correct, but it need more than 200 seconds, while VGGT only need 0.6 seconds. This is a significant difference, and all of these 3 results are very impressive. As for runtime and memory, These are also information I got from others slide deck. So the inference happens on a single NVIDIA H100 GPU with the flash attention V3 image. Like we mentioned previously, it's not like a high resolution image, it's only small 336 by 518. Overall, the memory usage scale roughly linear with the input frame, like it can handle even 100 frames. Time usage is around like ON 1.5. Finally, also the author also provide 3 limitations to this algorithm. First, it does not support fisheye or panoramic images. I think that is not a big concern, because why it didn't support fisheye? That's because that kind of image was not contained in the training data set. If we have that kind of image collected with ground truth annotation, we can add those images into training data sets, and the VGGT network is able to handle it. Second, reconstruction performance drop under conditions involve extreme input rotations. I think that's also not a big concern, since like we could add some pre-processing steps to detect extremely input rotations and correct them. Last, it fails in scenarios involve substantial non-rigid deformation. Because in the experiment part, also the author shows examples like people riding on a bicycle on a track. So in that video sequence involve motion, I think that is not that basically is like a non-rigid deformation. Anything that involve motion would not be non-rigid, but it looks like the algorithm VGGT is still able to handle that. Last, we may need some further short thoughts. So, in summary, it looks like this token-to-token relational reasoning through self-attention is able to discover these epipolar relations, feature matching, multi-view reconstruction, track associations. Here is what author claims. These geometric aware transformers, given these geometric aware transformers, you no longer have to be Zimmerman for 3D reconstruction. I don't know if Zimmerman agree, but AI really changed a lot. So does that mean we don't need to study these thick textbooks, understand all of the theories like epipolar stuff, multi-view geometry, triangulation, bundle adjustment, optimization, nonlinear optimization? We only need to understand how transformer works, how this data was collected and data set was built and handled, trained, feed through the network. Then we can do this 3D reconstruction. The authors claim 3D vision at the dawn of large-scale learning. So the idea is to let the model learn from ample quantities of 3D annotated data. This was inspired by the beta lesson from the reinforcement learning. Basically, this beta lesson is general methods that leverage computation are automatically the most effective. So that means given a problem, we don't need to design sophisticated algorithm to handle this case, that case, a lot of conditions like what we have tried in reinforcement learning. Don't do that. Just provide a general method, like just the vanilla reinforcement learning and some reward. Like if we are trying to teach a human to play pong, don't tell them when the ball approaching this way you need to hit that way, or you need to move that way in order to respond to that, like the ball approaching, you need to move this way, move that way. Don't do that. Just let the player play. Then at the end, told the player, okay, you win the game or you lose the game. Give the player reward at the end of the game. Then do nothing. Just let the player play in a general, like use a general method. Then at the end, the player will automatically provide the most effective response to play pong. So that is the beta lesson set. So does that means we don't need any of these things? We only need to collect. Now it seems no matter which field you are working on, you only need to collect tons of the data corresponding to your task and feed this data to a general, like transformer based network, and then the network is able to magically solve any type of the problem. I'm not sure if that is the case, but VGGT definitely inspired us to think the future of what will come in the field of computer vision. So that's all for our VGGT discussion. Thank you for listening.